Standard temperature and pressure, or STP, is a set of standard conditions for all gases. Although the name standard temperature and pressure implies that STP describes only temperature and pressure, STP actually describes temperature, volume, the number of molecules of gas, and pressure. At STP, these all have specific values at specific units. The temperature of a gas is 273 Kelvin, the volume of the gas occupies is 22.4 liters, there is 1 mole of molecules of the gas, and the pressure of the gas is 1 atmosphere. Or 101.3 kilopascals, or 760 millimeters of mercury, or 760 torr. These units of pressure all mean the same thing, but if you use the wrong units, you'll get the wrong answer. There are several basic laws that you'll have to know concerning the behavior of gases. Boyle's law states that when the volume of a gas decreases, the pressure increases. Charles' law states that if the temperature of a gas increases, the volume increases. Avogadro's hypothesis states that at equal temperatures and equal pressures, equal amounts of two different types of gases will take up the same volume. Gay-Lussac's law says that if the temperature increases, the pressure increases. Here's some dry ice in a sealed container. Now, the temperature is increasing, so you can probably guess what's happening to the pressure. All these laws deal with the same general ideas and can all be combined into the ideal gas law. Explosions aside, the ideal gas law takes all the relationships and all the previous laws that I mentioned and puts them all into one equation, which conveniently allows you to work with pressure, volume, temperature, and number of molecules all at the same time. Now, you may be wondering what the R in the combined gas law is. R is the universal gas constant. I don't know why it's an R, it just is, and you're going to have to know that. The universal gas constant can change depending on what units you're using, specifically what units you're using for pressure. You can calculate it by rearranging the combined gas law and inputting the values for STP. The universal gas constant does not change for anything but units, and is a constant value which you have to input into the ideal gas law equation to get everything to work properly. Speaking of the ideal gas law, you may be wondering what an ideal gas is. An ideal gas is a theoretical representation of a gas that is used to calculate the properties of a real gas using formulas like the ideal gas law. Laws concerning ideal gases work because of a few false assumptions about the atoms or molecules that make up a gas. These assumptions are that the molecules behave as rigid spheres, all collisions are 100% elastic, meaning there is no energy loss when molecules of the gas collide. It is also assumed that there are no intermolecular forces between molecules or atoms, and the particles have no volume. These assumptions are false, but don't make calculations inaccurate unless certain circumstances are met. If a gas is at very high pressure or very low temperature, it will not follow the ideal gas laws. This is some carbon dioxide at very high pressure and very low temperature that is behaving distinctly not like an ideal gas should. You may have noticed that there is both solid and liquid CO2 in the test tube with bubbles of gas coming out of the liquid. This is because the gas is at what is called the triple point. The triple point occurs at a specific temperature and pressure for any substance and allows for both a solid, liquid, and a gas to be present at the same time. The boiling point of a substance changes based on pressure. Boiling happens when the vapor pressure of a substance is equal to the atmospheric pressure being exerted on it. The vapor pressure is the amount of pressure exerted by an evaporating liquid on its surroundings. This means that if you boil water on your stove, the vapor pressure of the water is equal to 1 atmosphere. Diffusion is the process of a gas mixing with the environment around it. How fast this process happens is determined by how much the gas weighs. The lighter the gas, the faster it diffuses throughout an area. The rate of diffusion can be calculated with this formula, where R1 and R2 represent the two different rates of diffusion of the two different gases, and M1 and M2 represent the two molar masses of the two gases.